Welcome back to our series on neural networks for architects. On day 3 on things and numbers. Now we want to go to the tools Mathematica provides to implement encoders and decoders. So let's go in detail. First, these names of encoders and decoders, it's a little complicated and misleading, so there's a proper argumentation here. I just want to summarize it and give some indexes. So if you have a geometrical thinking around the harmony of reality, so this is what encoders and decoders are discussed towards everywhere. So then you have reality and you encode parts of reality to numbers, and then you decode numbers back to reality. So, and these things are good if the numbers are in harmony, if the numbers fit reality, so are part of reality. So the reality itself is a unity of everything. So we are, as we described all around, we are very unhappy with this view because it's not the quantum view of the 20th century, and which is driving all physics, mathematics, all biology, all computer science of 20th century, all the things we are struggling around and we are curious about. What I would suggest, and this is our understanding, with Wittgenstein or others, we algebraically equalize numbers with reality, and we don't say we know it totally, but we say it's the same. So then we have an obstacle. We don't point at a part of reality. We have an obstacle, and we go around. So therefore encryption and encoding is of the same type, because this is getting out of reality towards rationality, and this is what we equalize algebraically with characters. And this is what the neural networks are working on, or the aliens or the intelligence is working on. And then we bring it back towards reality, to the numbers. So the question is what the numbers are. Are they part of reality, or are they like reality? So, and our conception of information with Shannon and everybody is this communication scheme rotating around an obstacle and a universal axis and invariance. So this is the talk. So, and therefore encoders and decoders is a little tricky. We would say get it out of reality into the ratio and bring it back to reality and talk back. So therefore we get a picture, the reality shows, we get a picture, we talk, and reality hears what we are saying. So all these things will be developed, but nevertheless all systems with neural network work like this. Encoders goes to the network and go back with decoders. Encoders, network, decoders. This is how it works. Now let's have a look on the principal data formats, and there's a list of encoders and decoders and how they work. So let's so for example, this is an encoder to get images, whatever image you have, in a 128 by 128 grayscale. So this is like here, and you see a lot of different parameters, and there's a lot of automation there. So get a picture from the cloud. This is nonsense. Get Richter image. So, and now we simply use this as this encoder here as a function of this image, and we get a code, which is an array of 128 by 128. We can ask for the code dimensions of the code, and it's grayscale 128 by 128. So decode is just the other way around. We have here again some parameters. Look it up for details if you want to know more about decoders. Decode is again a function of the code, and then we get 128, 128 image. Of course, if we get this kind of reduction of the image, we can't get more out of it. So we lose proportion and so on. It needs some post-processing or more advanced self-programmed encoders that you at least keeps a proportion or whatever. So that's with images. You see the symmetry and how easy this is to use. Whatever picture you put in, ever format, whatever a color scheme you have and so on, it's just giving an array of 128 to 128. This is constant. This is what networks can work with. Give some result. If you want to have a result as an image, take a decoder, and there it is. So normally you don't have that image as a decoder. Normally you say this is a face or whatever. So classes. Similar to use. You say it's an encoder, it's of type class. Then you say we know two classes, male and female. This is a description. We have then encode, and we have a list of elements here, and we simply can say what is it, and encode, and they just give the index to the classes as we discussed about indexes on lists. The decoder is a little more complicated. We again say it's male and it's female. It's a decoder, get it back to reality. And here we need probabilities. We say for the first element we have 10% and 90% second, 60% first, 40% second, and this decoder says then, okay, if I'm 90% sure that it's female, I'm 60% sure that it's male, and delivers these two classes. These are encoders and decoders for classes and classification, or differentiation, as we'd seen and discussed before. For example, characters now. We discussed this with the ASCIIs and so on in detail. It's super simple to do. Encoder, characters, create the encoder, encode, what are you doing? You directly get all these ASCII characters. Decoder, characters, simply says this. It's working like with the classification. So therefore, we have a unit vector of all the ASCII numbers. It's 97. The unit vector says it's 0, all zeros, but the number 19 is 1. Therefore, we have it here. So therefore, we get the 90th element. It's the first one. The 90th is here. It's 1. And here's a 75. It's here. It's a 1. And this is the data, how it is delivered, and it's a question of classification. It works like classification, but then we have the two characters with a certain probability. So we always, we are never sure how things are, so there's certain probabilities, and we say, okay, we decide. So this is with classifications of characters, which is simply a list of 97 classes. Tokens. And you see, you don't have to be afraid of huge numbers of classes. This is an encoder, and he has 39,000 classes. So therefore, we can say here it's a matter of fact. These are the tokens we discussed. The number in the index of the lexica these are the indexical numbers. The decoders is a token, and this is a 39,000 vector, a dimensional vector, and therefore we do the same to get this thing here back. We do the same unit vector, 39,000 zeros, the 11th one is a 1, and the same thing if we decode that, a matter, and so on. We are there. Good. This is with tokens. So you see it's all the same, but specific sets of classes. You can make this class by yourself. Characters and tokens are a predefined set of classes, but works the same. A little more, we had an extensive discussion about audio. You do it like the images. It's audio, we have a sampling rate and say this is an encoder. So we give it a certain resolution and simply get an encoder, which means let's just make it here to be fast. We get an audio object from the cloud. This audio are the birds. We code this and get a list of, you see it's different in cloud. We get a list of 30,000 numbers. This is our audio, and if we want to hear that, there's no decoder for audio yet. You have to implement it by yourself. But to get the code to your ear, make an audio on. There you see these are the lists. Each number is a list because there's only one channel, and if you want to have stereo, then you need a second channel. You can have 16 channels if you like. This is within this. To make that mono, you have to flatten that audio sample rate as we had it here, and this is our decoder, and we can render it back, but it's not implemented as a general device in Mathematica yet. So if you, as we discussed, if you go with Fourier to get an image of the sound, which is appropriate, you can't make good reason on these geometrical, on this line of numbers in geometry. You need the harmony line and make a picture of that. Then we have the sound. We make a net encoder, and this is called audio melt spectrogram. Very simple. So just we have the code as we did with the audio. Was it out? Yeah, it was out. We have the code. It's still the same. No, it's different here. So this is another setup. So now we are with a spectrogram. So this is a spectrogram. If we want this to see, this is decoder is not there, but this is the spectrogram. This is a rendering of the spectrogram. We do that with a matrix plot, and we give that with a logarithm. That's the, you have to transpose the logarithm here to render it and not getting. Now this is complicated with the with the frequencies, that they are not. Decoding is always like this, and it has an exponential, the encoding in it. To make it inverse, you need the logarithm. So you see it getting very simple to use in standard cases. There are more of these. If you want to see the documentation, just take an encoder, go here, and you have the encoder. These are the Boolean, and these are the discussions on encoders, character class, we had that image 3D token. Instead of characters, we have the UTF. So these are 100,000 different kinds of audios and subword tokens. So can look it up, and it's getting updated frequently because this is in development in these times. Very important. So if, as we'd seen and discussed in the previous chapters, that you have to write your own encoders and decoders because things are not so standardized, and there's a lot of fantasy and potential in there, tweaking and turning, you're getting certain glasses as your aliens at the edge of the world. This, for example, is how to write an encoder with your own function. So therefore it's an encoder, it's a function, and then you create a pure function and say how many numbers are the result. So this is an encoder, it's working in this part, it's part of the system, and then we can go with any number and transfer an RGB to HUE. We discussed this is a physical color, and this is a physiological number. And with a physiological number, you can do arithmetics, which is plausible for your eyes, for your reception, as we had it with the reflective and projective numbers, like with Grassmann. So if you have a decoder with your own function, it's just the same decoder function, color converted, hue to RGB. If you want to have it back to RGB, take the decoder on code and on data. We did it with data. This is data, then you get the red. Yeah, as an RGB color, so we can have, for example, first normal, I don't know. Okay, RGB, here we are, on 00. Okay, that's with the function. And this is how to use it. So, and I hope you get an understanding that it's super tricky to, if you just follow, and all our effort here is that you, on the one hand, it's good to have the encoder and decoders and to know that they are working, but you always follow then a standardized path, and it's not good towards understanding what is going on. So the what question is always a kind of hidden then. What is going on there, and not, and this always tends to work to say it's used, it's a tool for using it like this and this to solve a problem, which is not the case as we've seen here. This is problem solving, this is embracing of obstacles. This is the how question, this is the what question, the architectural one, the engineering one. So that's it for today, and see you in the next tutorial.